My name is Alex Tarnava. I am the founder and CEO of Drink HRW. We have the IP and I am the primary inventor of the open cup molecular hydrogen tablet. Today I have a special guest, Tyler Lebaron. Tyler is the executive director of the Molecular Hydrogen Institute. He's involved in various hydrogen organizations across Europe and Asia. And from my perspective, he's the leading hydrogen researcher here in North America. So welcome, Tyler.
Thank you. Nice to be here.
First off, I just want to thank you for being so skeptical of what we were doing in the early days a few years ago. Without you questioning us and second guessing us, we wouldn't have been pushed to attempt to falsify everything we were doing so extensively, replicate it so extensively. In that process of trying to keep our credibility, we actually understood the process a lot better and were able to make a better product. So your skepticism really drove a lot of our R&D.
Well, yeah, I mean, you know, when you first came to me, what is it, several years ago, saying that you can get, you know, this 10 ppm, 10 milligrams per liter, when of course the saturation of hydrogen gas at SATP is only 1.6 milligrams per liter, 0.8 millimolar, and you're getting 3 and 4 times this concentration, and without the pressure. Yeah, that's yeah, it's still difficult to believe, and I don't know that we really understand why, but I guess we can measure it, you know, and that's the thing. As scientists, we can say, okay, we can actually measure gas evolution. When I was in Beijing at the university there, we're doing research collaboration, published some articles together, but I use a tablet and put it in there, and we test the concentration, and sure enough, it's very high, and we can see this, and of course it makes sense stoichiometrically, but you know, I think as I've taught before, we try to understand the micro and nano bubbles and this this quasi bubble formation in the water.
Of course, because our cloud of hydrogen gas above that, and actually interestingly, as you've observed, maybe something about the cloud increases the internal pressure, because our actual reading of dissolved is higher than 1.6 when we measure it, but then the cloud isn't quite dissolved. It's something in between. It's quasi-dissolved nanobubbles, so they tend to linger in suspension. They're not dissipating, but they're not dissolving without the accompanying pressure, and that's actually something that we've been able to do, is when we pressurize the cloud, it saturates. And that was one of the replications and attempts to falsify that we did when Tyler was really pressing
I asked you, I said, okay, if you really have something, then do these experiments. And then you did them, and I still didn't believe it. It's like, okay, send me the tablet, and I'm going to do the experiments, because I want to see. And you're right, when you look at, it doesn't contradict Henry's law. Henry's law is very much involved in how the bubbles work. And you have, you know, Laplace equation, and you have different ways of understanding, you know, nanobubble, the Ostwald ripening phenomena, and how the gases will, the internal pressure of these bubbles can get, you know, hundreds of psi. Yeah. And so there's going to be an equilibrium diffusion gradient, and they're either going to be growing or shrinking or coalescing, and that's going on. And anyway, it's really interesting. You know, we need to do some more, you know, laser backscattering analysis or something to understand what the phenomena is.
We have done that, and we know, you know, the first burst and the second burst, and how small these nanobubbles are, and how much it plays a role as a nanobubble starts to grow.
I did see the data. I did see the data on the nanobubbles with the laser. That was interesting. That was help to clarify and elucidate what's going on. Yeah.
Great. And now, when I got into this, I got into it for my own health, you know, as you and I have talked about, and myself and my founding partner, Dr. Holland, who's a medicinal chemist, we wanted to get this out there to the population.
So isn't he in the pharmaceutical industry?
Yeah, so he's in creativity. He creates molecules for drug candidates in the pharmaceutical industry. So he's pretty heavily involved. When I met him, the project he was working on that I believe is now going down the drug pipeline was a cure for hepatitis B through, you know, various small molecules, right, and a few of them in conjunction. So that's what he does. He deals with small molecules. It doesn't get smaller than hydrogen. Right?
Yeah, that's true. Smallest molecule in the universe.
Exactly, right? So when at first I was just hiring him to review everything I was doing to make sure it was safe, and then he actually came to me and wanted to get involved as he was reviewing the research and the literature. He went from being more skeptical than you were about our tablets, about hydrogen in general, to wanting to be a partner and get involved to get this out there for people.
Well, I was going to say, coming from, if he understands, molecular biology and pharmaceuticals and understanding, it's a big thing. When you look at science, we typically understand there's one drug, there's one target, there's one disease, there's one organ. And here we're talking about hydrogen that's, pleiotropic, all these different organs, all these different effects, all these different targets. Oh, but we don't know what the actual target is. Yeah, that's a pretty big problem when it comes to this type of science. And it's a huge
red flag for scientists and
I'm surprised that he even got involved, because that's kind of cool. That
typically, when anything proposes to be a panacea, it's a huge red flag. I was skeptical of hydrogen. That's actually how I got interested in. I had a lot of my former staff who were selling a certain brand of water ionizers that were claiming miracles, and it really
isn't that
upset
why
me.
You contacted me in the first place?
It is, and I was debunking a lot of what they were doing. But then we started talking about the hydrogen. I'd already read a bit about hydrogen at that point from a few years back, if you recall from our early discussions.
Look, it's coming back. That's funny.
And I started becoming more and more interested in hydrogen, and that's how I went down that path. Of course, I bought an ionizer, but then upon testing, there was no hydrogen being dissolved in the water. You didn't have
the right source water to get the hydrogen.
And so there's 2 points I want to talk about from what we're talking about. First, when that happened and I found I wasn't getting hydrogen from the ionizers, I started looking into the best methods to create hydrogen, and magnesium kept on popping up in the research. Now, from my understanding, upwards of 80% of North Americans are deficient in magnesium, and our reaction is leaving free magnesium ions, which we have from the water chemistry that we've done, which are highly bioavailable, better than most salts, but yet there's certain parties, there's a ready-to-drink company, there's certain companies in Japan which attack magnesium and say that it's not good to put in the water. Now, do you have any thoughts on that? Because we want to have the best product out there for the consumers, and it doesn't make any sense to me why magnesium would be dangerous to consume in the water. It doesn't make any sense to, Dr. Holland, but you've been involved in this a lot longer than we have.
Well, I mean, I can understand the concern, because first off, it's not really approved by the Japanese government and as a food additive, and so that's when I was in Japan doing research. That's one of the things that we talked about, but it's also not approved by the FDA or in Europe or anywhere else.
The FDA doesn't approve any products, and so we're actually the only company in hydrogen who's filed our NDIN, which is a new dietary ingredient notification. So we're actually the only company in the industry that's selling hydrogen products as a supplement that's met our legal obligation with the FDA. We're going through the GRAS process right now. We filed class 3s in Canada, we filed in Europe. So we're trying to do things. I mean, my partner is from the pharmaceutical industry. Everything is to the regulatory book that we're trying to do. And all of my consultants say this is incredibly safe. The safety data on this is well beyond what's needed. But yet you get some people saying the ready-to-drink industry in Japan that
it's part of because of these policies, right? And yeah, people misunderstand. Okay, like you said, the FDA doesn't really approve any supplements. That's not what they do. It's food and drugs. Yeah. And so because it's not approved, well, Japanese has the same laws. Europe has the same laws. This is very common, and so. I can understand some concerns because you're talking about magnesium metal, and so that can kind of get people concerned, like, hey, this is going to be a metal. But I think it's important to consider that when the magnesium does react and you produce magnesium ions and hydrogen gas, which I mean, magnesium ions are the only atom or the only element that is going to be bioavailable to use in the body as an ion.
For our users, what this means is when you take in a magnesium supplement, say you take in magnesium oxide, what your stomach acid, your gastric acid first has to do is it has to break the bond between the magnesium and the oxide. Without doing this, it's just a laxative. It just goes right through your system. Now, in vivo studies and in-person studies have shown the average person can only take in about 4% of magnesium oxide. The rest just passes right through your system because it's such a strong bond. Now, magnesium oxide is by a landslide the most common form of supplementation. So when we're delivering these magnesium ions, which is what our body actually needs and the only thing it can take in,
and absorb and use, yeah.
Our 80 milligrams, theoretically are 25 times more potent than the magnesium oxide. So our 80 milligrams could be like taking a couple grams of magnesium oxide without the heavy laxative effect.
Yeah, it's a good way to put it. And so, yeah, I go into your question though, as far as the concerns. I think first off, the fact is that people get confused between policy and science, and so they think that there's an issue there. But safety-wise, yeah, magnesium, this form of magnesium has been used in studies back in the 1980s even, where they administered several hundred milligrams of the magnesium
to measure hydrogen gas
for hydrochloric acid production. Very safe. It's actually been used for implants, biomedical implants and alloys and like bolts and screws and different places. And it's interesting, this is one of the really neat things. They've been doing this, for like a century. But when you look through the research and they'll talk about the benefits of using these magnesium, the same magnesium you're using in your tablet, but they'll put this alloy and they'll put it inside of the body, and then they'll be surprised because there's such a low amount of inflammation and of all these benefits. Like, wow, this really is accepted by the body so well. I wonder why that is. And now, decades later, we're finding that hydrogen gas has these anti-inflammatory and antioxidant-like effects that could explain why these magnesium alloys that were directly put inside of the body were so safe and had no problem, no kidney issues, it doesn't form some sort of salts or cause any problems like that. So anyway, I think that does also help with just the concern that maybe taking these tablets or taking the magnesium, whatever form, because there's magnesium sticks, there's other ways to do it. I think the only legitimate concern that I would have is the purity of the magnesium. I think some people that, we'll just get it from whichever place. Well, maybe it's not. I know you could probably speak better.
That's one thing.
Than I can.
We spent a year sourcing, the magnesium we're using, getting the exact particle shapes and sizes needed for it. Absolutely. I mean, there's only a few sources of magnesium in the world to get this elemental magnesium, and a lot of the countries that produce it have incredibly high levels of heavy metals. Right, that would automatically fail the product. We've tested other products that aren't ours on the market and have data seeing that they're in direct violation with, say, California Prop 65, because the source of magnesium is a concern, the purity is a concern for the heavy metals that could be in. So it's something we're keenly aware of. We track, we don't just test the heavy metals, we test all trace metals, right, in our magnesium. So we're very aware, and it's part of the safety data we need for submitting things to the FDA, like our new dietary ingredient notification, right, which we're the only company that produces these open cup tablets. Well, we produce open cup tablets. We're the only ones who have filed our new dietary ingredient notification, which is a legal obligation in the United States. So this is part of the safety that we need to ensure, right? So yeah,
so scientifically, yeah, there just doesn't make any sense that it would cause any problem for the body, and this has been demonstrated for over 100 years. And the amount of magnesium is very low. Yeah. How much your tablets? You said that
there's 80, there's 60.
Okay, less than 100 milligrams, and most supplements probably contain more magnesium than that. So I think the only legitimate concern would be the safety, the purity of the magnesium where people get it at.
Exactly. Now, you mentioned antioxidant-like effects and anti-inflammatory-like effects. I want to touch base on this, and I want to circle back to what we said, that a red flag for skeptics, for true scientists, everything, is when something claims to be a panacea. Now, hydrogen, if I'm understanding this correct, it's not actually an anti-inflammatory at all. It's not actually an antioxidant, but rather it affects our gene expression, and it regulates production of pro-inflammatory cytokines. It regulates, via our NRF2 pathway, production of our endogenous antioxidants like, glutathione, superoxide dismutase, catalase. And along with a lot of other benefits, what this makes hydrogen is, I don't like using the word, because usually people using the word are claiming a lot of miracle benefits, but it really seems to be sort of like an adaptogen type substance. I know that there's data when you put a hydrogen-rich medium on a healthy cell, nothing happens. Nothing changes, but then you artificially damage the cell and you see the markers.
Yeah, well, okay.
So can you expand on this?
Yeah, so a couple of things. First, it's in our definitions.
Yeah.
An antioxidant, from a chemistry definition, we could say, that is something that donates an electron or gives itself, sacrifices itself for a radical donation. There's an actual oxidation reduction reaction, and that would be the definition of an antioxidant from a chemical perspective. Yeah. It's really not a very good definition for physiology, for what really matters in biology. A better definition would be something that improves the redox status of the cell. Okay. And so by this case, like exercise could be considered an antioxidant. Typically most antioxidants and things that are good for us that's how they work, not by directly scavenging and directly, they can neutralize and react with radicals, yes, but it's really improving the redox status of the cell. And so if we use that as our definition of an antioxidant, well then yes, hydrogen is a great antioxidant. But typically you see these diagrams of like free radical is missing an electron, and then an antioxidant has an electron, and then there's an electron donation. It's really not very accurate. It's a very rare case that actually happens. Many free radicals have too many electrons. I mean, superoxide anion radical, for example, is not an oxidant. It's a very powerful reductant, and so that has an extra electron, which makes it extremely reactive. It's an unpaired. That's the definition of free radical, is an unpaired electron. Oxygen gas that we breathe it's a radical. It's a diradical, has 2 electrons, and we wouldn't need to go into that. But I'm just saying that there's an oversimplification. So when we look at hydrogen gas, same thing with anti-inflammatory. We can give some different definitions of that. But I like to say antioxidant-like effects and anti-inflammatory-like effects because I don't want.
But only if they're dysregulated, correct? Like if someone
okay.
doesn't have excess inflammation, it's not like a non-steroidal anti-inflammatory or corticosteroids that just blocks it. Exactly. It seems to regulate production of our pro-inflammatory cytokines, which is what leads to inflammation. Yeah. Right. So if you take a healthy population, it's not going to have an anti-inflammatory-like effect. Typically, at least not statistically significant.
Yeah. I mean, not compared to, say, a stronger pharmaceutical agent, right? Yeah. I mean, I want to talk about when you give hydrogen gas to a healthy cell. I often do say the same thing, that you really don't see anything. That's often true. So it depends on the cell. Okay. Sometimes hepatocytes, they seem to be more sensitive to hydrogen. You do see changes, and you can see changes in gene expression, in microarray analysis. You can see, actually, there's really interesting changes we just found out, but I won't talk about it now. But so we can see some things, but often you do need to have some sort of assault, to bring it out of homeostasis. Yeah. You need to perturb it out of homeostasis, and that's when you see the rescue effect. You see the upregulation of your glutathione level. So that's probably a good example. So glutathione, of course, your body's endogenous antioxidants, one of the primary ones. You need to have it at a certain level, and if it goes too high, then that's reductive stress, and you can have reductive stress. Yeah. This has been demonstrated. In fact,
one of
the
biggest negative claims against antioxidant therapy that's been prevalent for 20 years was that taking in too much exogenous antioxidants actually had an opposite effect, and it blunted production of our endogenous from within antioxidants, and we went off balance again. So it's about balancing our redox, if I'm understanding it correct, rather than.
So I just submitted a paper on this, but I don't know that we understand all the real reasons why the clinical studies have shown that ingestion of high levels of exogenous antioxidants, whether it be beta carotene, vitamin E, or vitamin C, or whatever it is, essentially led to an increased mortality, and people are getting cancer and dying faster, and so they actually stopped the clinical studies. Probably has something to do with it does not help does not help improve the redox homeostasis of the cell. In fact, it can actually exacerbate it, and we don't know exactly why or how that's working, but we just see the reasons for that. Now, we could go into a discussion, well, yeah, but all those supplements they were using, they were already oxidized, or they weren't in this natural form. Be that as it may, the fact is they were actually
damaging. They were harmful.
Yeah, they were harmful, right. And they were still considered reductive molecules. So therefore, they still had those effects. So we can't begrudge the observation either, and we can't do this post hoc illogical fallacy.
And this is why I don't like calling hydrogen an antioxidant, because of the common definitions, lumping it in with these other antioxidants, because hydrogen really doesn't work in the same way.
Yeah, it's more like exercise. It's if anything, my personal opinion, it's more kind of a pro-oxidant. Actually, there's some data that hydrogen actually acts as a mitohormetic effector. In other words, so in the mitochondria, that's the powerhouse of the cell, right? And in a lot of ways, the brains of the cell, even more than like the nucleus and the DNA. The mitochondria they are very important, and hydrogen gas can transiently increase low amounts of superoxide production, which not enough to harm the cell, not enough to hurt it, but just enough to drive it into stronger production of so glutathione levels. It activates the phase 2 enzymes like NRF2 pathway, which regulates over 200 cytoprotective proteins. So it's very beneficial. But we have this transiently small increase, and then we have this increase in all these cytoprotective proteins. And that's exactly what exercise does. In fact, we just published another paper where inhalation of hydrogen gas, we actually, this is really interesting, but in this case, hydrogen actually increased markers of oxidative stress, just a little bit, about, I think it was 16%, which is comparable to, say, a normal bout of exercise, which when you look at diseases, typically the increase is like 300, 400%.
It's like an exercise mimetic then, a little.
Yeah, that's kind of what my paper was positioning. When we looked, based on the biomedical and clinical effects of molecular hydrogen, yeah, it seems that hydrogen has like this exercise mimetic, because it not only can it preserve and perhaps potentiate the benefits of exercise, but perhaps it can actually activate some of the same transcription factors that exercise alone does anyways.
And for our viewers, we do have some easy pages and analogies on what we're talking about. There's a video on redox, and we've got some scales going showing that it's about balancing. So hydrogen has shown to both increase, oxidative stress and
although
decrease.
Balance is not a good word either.
Well, I'm trying to be simple.
I know, I'm just saying, because balance, we're homeostasis is where we need to be, which is not. Yeah. Anyway, but go on.
It's sort of my understanding the same thing for regulating our inflammatory system. And for our viewers, we need inflammation. Inflammation is...
Yeah, it's the same thing as free radicals. That they mediate. When you get sick, it's inflammation. It's everything that gets you to recover, wound healing. It mediates the benefits.
So it's when it's dysregulated, when it's out of homeostasis.
Yeah, dyshomeostasis.
That's when the issue is. Now, for viewers who aren't aware, Tyler knows a lot about sports science. On top of being a world-leading researcher in hydrogen, he actually got his master's in exercise and sports science.
Yeah, I like exercise.
I mean, this guy, he runs like a 2:30 marathon, and he is huge into fitness. And one of my initial concerns with hydrogen and exercise, because I exercise was my life, competition was my life, and it is still the biggest concern of most of my friends, is antioxidants usually aren't to be used in conjunction with exercise for blunting effects. Now, what we've talked about on how hydrogen acts a little different than most antioxidants, and it's, as we've talked about just now, is exercise mimetic. What is hydrogen's relationship with exercise? Because there's quite a number of clinical trials showing improvement, including ones on our tablets.
Yeah. So I think it's an important point. When we look at the research on just conventional antioxidants, they're equivocal. Sometimes there's a blunting effect, sometimes there's no effect. I guess sometimes there is a positive effect, but sometimes the antioxidants that are using, they're not just normal radical scavengers. They actually exist in the cell as effectors of signal transduction, and they're sensors and modulates redox homeostasis like resveratrol. It's not just just go in there and kick out the bad guys.
Well, there's one study I read from Russia, hypothesizing that resveratrol actually works by creating H2 inside the mitochondria.
Yeah, I saw that in the American Chemical Society posted an article. Yeah, that there's a postulation that it's in the mitochondria, resveratrol through a 2-electron dissociation attachment produces hydrogen gas, and hydrogen gas then mediates the benefits of resveratrol. Very interesting. I don't know if I believe it, but it's pretty. It's.
I thought I'd bring it up when you mentioned resveratrol.
Yeah, it is kind of interesting. Anyway, we don't want to go into that, but. Going back to the main question, okay, so how does hydrogen gas then differ as this antioxidant effects compared to, say, other antioxidants? Do we run the risk of potentially blunting the effects? And I think it goes part to our conversation that unless there's a real stress there that's toxic, hydrogen gas isn't going to do very much. Hydrogen gas helps keep things in the hormetic response. So it'll diminish an excessive amount of stress, but not just negate it, so that you still get this hormetic. Do you know hormesis?
Yeah, it's exposing yourself to a toxin for a beneficial result. I mean, even it's used by practitioners now with, say, nut allergies. If your child has a nut allergy and you start by touching them with the nut they're allergic to, over time, you're no longer
okay,
allergic.
I'm not familiar with, but it says same thing. Yeah, just small amounts of stress lead to induction of cytoprotective proteins, and you get
what exercise is. It is damage. I mean, and interestingly, exercise and cold exposure, extreme cold exposure, both
and heat exposure,
irisin, which drives a lot of the benefits.
The heat shock proteins. Yeah. In fact, hydrogen gas can also induces heat shock proteins. And also induces MTPR, which is the mitochondrial unfolded protein response. So again, this is potentially part of the hormesis effect of molecular hydrogen. So yeah, hydrogen is going to have some of these benefits that are more similar to exercise and activating some of these same transcription factors, which is why we can say as an exercise mimetic, and really doesn't run the risk of blunting the benefits of exercise, but perhaps potentiating them.
There was a good study that was published out of Brazil. It wasn't on humans, it was on mice, I believe.
Yeah, the inhalation of hydrogen gas.
And I felt it talked about some of this stuff a little bit better than some of the human studies.
Because they did some really well controls. Yeah, it was a very interesting study. They actually inhaled hydrogen gas while they were exercising. Yeah. And yeah, it showed that it actually potentiated the increase in superoxide dismutase. That's very important antioxidant in the body, but it didn't impair exercise performance at all, which is good. But it did help to attenuate very high levels of inflammation. There's a faster recovery, for example, and that's what we're seeing. Similar things in the human studies as well. In the study that I did recently, that's published on actually using your tablets. Yeah. Thank you again for donating that.
No problem.
So we didn't have the opportunity actually to measure various biomarkers, to do biopsy or things, but we just did a very short, simple pilot study. It was a double-blinded, randomized, placebo-controlled trial.
Crossover.
And it was a crossover. So just so the viewers understand, so we did. We took, we had 20 patients, 20 people, subjects, healthy individuals, and it turned out only being 19 when we did the study, because something happened with one of them, and then we all got their baseline, figured out where they were at, what their VO2 max was at. They went through the whole protocol, they got familiar with everything, and they. Just so there was no learning effect and everything, right? Did that first, and then we just randomized them, and half of them took hydrogen and the other half did not. And then the next week we tested them again.
And for the viewers, the placebo was actually a magnesium supplement to account for any effect that magnesium could have had on it. So.
There was it was very well controlled. In fact, the researchers, myself as well as those who helped me do it, we didn't know which ones until after we compared the two. Until after we compared the two, did all the statistical analysis and everything, and then then we asked you, okay, which one was one and which one was two?
And You guys actually found an interesting result, and it's something that I've noticed on myself when I go to do cardio and I take a high dose of hydrogen, that I can't actually get into my cardio zone. It takes a lot more work. It lowers my heart rate, and that's kind of what you guys found in the study.
Yeah, well, just that, we found that there was a decrease in submaximal exercise and heart rate. So it didn't blunt the maximal heart rate. Everyone still reached their maximal heart rate. We were doing the Borg's rate of preceded exertion, but through some, we weren't able to collect enough data. But it did look like it was easier for them to exercise. They wanted to push themselves harder and things as well. But we did see that, hey, during these submaximal levels, their heart rates were on average like 5 beats lower, which could be significant. I mean, we needed more research to understand the practical significance. But as a runner myself,
I was just going to ask, as an endurance athlete, that's what struck me the most, is that endurance athletes would probably see a benefit here. Maybe even people who do higher intensity interval that have to go round after round, like boxers,
repeated bouts.
Mixed martial artists, etc., even CrossFit competitors. Right. Lower heart rate might help you be calmer.
Yeah, so that's kind of why I wanted to do my study, so we could understand where hydrogen gas would be more beneficial. We were looking at a maximal. We did a full VO2 max. I mean, they ran until they could not run anymore. They had to have this heart rate. They had to have a total plateau in oxygen consumption. We had the gas mask on. We were measuring O2 consumption and everything. And they had to reach all these criteria for them to, know that they reached that. And yeah, when we look at the data, I think it makes more sense for these extended, repeated bouts of exercise. But again, we didn't do chronic supplementation. It was
acute.
It was acute. They just took it the day before and the day of the test, know. And now we just did another study, 159 subjects out of Japan. And they also did acute, but they drank the hydrogen-rich water right before exercise, and I think that could even be important. Well, I don't know.
I find it's a dramatic difference for myself, and this is just completely anecdotal, but for myself, I find a very high dose immediately before exercise, within 5-10 minutes, has a much better effect.
That almost seems to be what these other studies shows also. But now it's difficult to understand the mechanism, because signal transduction takes, half an hour or more when we look at cell culture. And so there's something going on that is very interesting.
Which is part of, the issues in hydrogen research, in my understanding, is it's proving to be so complicated, and a lot of the results don't make sense from what the last result made. But it's just, over time, there's tons of research teams across the world and universities all getting these positive benefits, and we're slowly learning. And as we're learning, we're actually disproving previous beliefs as our knowledge is expanding, which is how science is supposed to work.
That's how science works. And to be honest, sometimes when I look at our research that we're doing or others, sometimes I get these bout of skepticism, like, do I believe any of this stuff? I'm just like, this is ridiculous, and I think if people ask me, what is the best evidence that you have, on proving that hydrogen works? I'm like, okay, first off, that
you don't prove something works.
Yeah, that belies the very definition of science.
Basically, in science, you can never prove something works. Science's job is to falsify claims.
Yeah, prove it false.
And if you cannot prove it false,
it increases the probability that that it might be true.
Yeah.
At least that's how science works. But everyone has a different subjective. I was visiting with some researchers the other day at one of the universities here in California, which is why I came down here. Which is kind of neat that we were able to connect. But I was talking with them, and they're biochemistry and molecular biology researchers, and they're finding results in their lab on molecular hydrogen. They're like, yeah, it works. It works actually as well as what we normally use, and together it works even better. And they're pretty surprised. And so we were talking about this, and we were going on, and they're like, well, okay, we need to look at what are the clinical effects of hydrogen gas. See, if we can prove, again, I use the word prove, but if we can,
I was gonna stop you.
I know, please do, right? If we can show that that there's some effects in clinical studies of hydrogen, then we can try to figure out, okay, how's this working on this cellular level? Because clinical effects and how something works in vivo in the human body is very different than how it works in the cell, in cell culture, you know, in cell tissues.
And even, I mean, what is it, 1% of molecules that work really well in smaller mammals like rodents transfer those benefits to humans. So
yeah,
it's why you always see in the news a study comes out that mice have been cured of aging or cured of this or cured of that.
We've cured mice of pretty much every disease.
Exactly, and then a few years later you find it just has fallen flat on humans, and that's one of the interesting things.
Or you don't hear about it in humans.
Exactly, because and that's a big problem in not publishing studies. There's actually a movement going on, All Trials. I encourage everyone to search up All Trials campaign and sign it. It should be illegal for research teams to
register
not publish.
And then not.
Exactly, right? Because if we're throwing away all the studies without publication, then we don't know what works because we're only doing half the data. And that's actually what I want to talk to you.
Or they only publish the studies that do work, and then we get this false impression that some therapy
What if a team changes the goalposts 10 times and they run a study 10 times to find a positive result? Well, realistically, that's 9 times it didn't work, and they had to skew the data and everything involved in it to get it to work, and that tells us that that doesn't work. And that's why I have been partnering with public teams. I don't have any agreements to not publish data on any of the trials
that was our agreement.
I want to know what works and how it works. That's what science's purpose is. And I got into this. I'm passionate about science. That's why I'm telling everyone, go to All Trials campaign, sign the petition, because we need to know what works. We can't have companies doing these private studies and distorting the data. Right, and it gets into my next question, because this can distort data quite a bit also. Now, in distributing millions of tablets, tens of millions of tablets across the world, I'm noticing, and it's not exactly scientific, but I'm seeing a trend in responder versus non-responder. Right, some people seem to be responding a lot better than others. And for instance, in a responder versus non-responder sense, what could be incredibly significant to half the people, even 70% of the people, when you put in 30% of people who don't respond, the results can be insignificant. And we saw that in that mild cognitive impairment study. I believe it was the APOE4 gene.
There was the APOE4 genotype.
Wasn't it non-significant for the whole study, but people with that gene, it was incredibly significant?
Yeah.
And so mild cognitive impairment is kind of right before Alzheimer's dementia. Can you talk at all about, have you seen anything on responders, non-responders? Do you have any thoughts? I know I'm asking you to stretch from, research and just a hunch or anything.
Well, I don't know. I mean, my initial thought, if you were to ask me, I guess what you are, is I'd want to say, well, some people are more susceptible to the placebo effect than others. But it does seem that some people, okay, you mentioned people get head rushes sometimes.
Yes, and it's something I wanted to ask you about, because there doesn't seem to be any, published literature on this boost in energy, but over and over again, the biggest, responses we get from people is they tried their first tablet, maybe after work on a day, and they got a head rush, their head tingled, and they got a burst of energy and redid their day. And to me, that's placebo, but I experience it myself every time I change my dosing protocol. So myself, we still need to know a lot about proper dosing, when to take hydrogen, how to take it. And what I do just to play around is every few months I do a few-day washout, and then I change my dosing. I take tablets at different times of the day in different quantities of water.
So you want your customers to stop taking your tablets?
I'm trying it myself just for a few days. I mean, it's interesting, and every time I change my dosing protocol,
no, you're a good salesman.
I do get a head rush, and I know that even though I'm aware of the placebo effect and I'm, always talk about it, I can still be susceptible of it
yeah, well,
when
it's
I'm
interesting
aware
when
of it.
you when it's the repeatability is very high.
Yeah.
And I have noticed people do get this. Some people are just more susceptible or benefit to the benefits of hydrogen. And at the symposium, let's see, it was in 2015 or 16 in Japan. It was all in Japanese, so I didn't understand all of it. But one of them talked about somewhat of this effect that some people, and maybe it's more common, I don't know if you've heard this very much, but some people when they drink hydrogen water, they get like a flushing in the face and like just like this like peripheral vasodilation or something that happens. And it happens, I guess, what they felt, more people in Japan, they tried this water and the hydrogen water, and they would get this effect, and they kind of reported on some of the increase in like endothelial nitric oxide synthase and just some of the different effects that some people would get, which would account for some of this flushing effect.
And for our viewers, one of the reasons that there hasn't been a lot of study on responders versus non-responders is that these are large undertakings in science. It could cost hundreds of thousands of dollars to do a responder versus
it could be more than that
study.
To do a real.
So we've been working with public teams to study what they want to see, and often they don't have the funding to do a responder versus non-responder. And when I've talked to some of these professors, they say it does appear that it works better in some people than others, even in the data, but we need to do a lot bigger.
Yeah, or else it looks like you're just cherry picking the data or something.
Exactly.
So you have to be very careful when we do
that's why I asked you about the MCI, mild cognitive impairment study, because that was the first one where they isolated the gene that responded a lot better.
And I don't know what that really means. So in another study with dementia with hydrogen gas, in this case they inhaled hydrogen gas. Yeah. They didn't. I don't think they looked at the gene markers, but everybody had major benefits.
Well, overall there was a statistical significance, and that's why I mentioned, even say things in like systematic reviews on omega-3 when they're including studies in a healthy population that doesn't work within an unhealthy population. All of a sudden, it's not statistically significant because you're combining data.
That's like saying, vitamin C isn't significant because it doesn't benefit it. Okay, if you already have vitamin C, you're not gonna get pellagra or something.
Exactly. It's one of the logical fallacies that I really detest in the supplement industry is they'll prey on data and they'll be like, vitamin D deficiency causes brittle bones and hair loss and all these things. So supplementing in 10 times the dose will improve your bones and your hair and all this stuff. And that's just not true. A deficiency can cause an issue with something, but an increase doesn't necessarily cause a benefit.
Right.
In the same thing. Actually, there's a lot of cases where the opposite is true, where a deficiency causes something to go awry, and then overconsumption causes the same thing to deteriorate.
Yeah, that's absolutely true. And of course, you have to be careful because sometimes when you look at the RDA or the DRI, that's a statistical population. So some people may need higher amounts than what the DRI says. Because again, this is statistical. When you look at nutrition, that's how it works. So people use that understanding, that have a very small amount of understanding of that, and somehow extrapolate that to taking, hundreds and hundreds of times the mega doses in IV. This is what we need, and that could be, especially done long term, could certainly be damaging.
Absolutely, and I want to ask you, from my perspective, there's I think 61, 62 now published human trials. There's only a couple where there was no benefit shown. One was that recent Parkinson's study, and when I bought the study and read it, the placebo group was actually drinking hydrogen water too. It seems they messed up a little bit.
Oh, that one. I thought you meant ours, because we just published one too. We didn't see any benefit in Parkinson's.
Okay.
But that was a very short. Ours was inhalation of hydrogen gas, and it was just very short. We were trying to mimic the effects of.
That's interesting, because the rodent study showed that in Parkinson's disease, that continuous inhalation didn't work where water did work.
So that one, hydrogen water was the most effective. Continuous exposure
was not
effective at all, which we have seen in a lot of that data is not even published, but we just know that continuous exposure of hydrogen isn't very effective.
Yeah.
And which anyway, I was going to call that cell culture, but that's a different story.
Yeah.
Okay, but then they did intermittent exposure of
Which
hydrogen,
was a little bit effective,
and that
but
was
not as good as
effective.
water.
Well, so we tried to mimic the pharmacokinetic profile of hydrogen through inhalation of hydrogen gas, and so they only inhaled a very small amount of hydrogen gas for just 10 minutes twice a day, and it was a short study. It was 4 weeks. It was double-blinded, placebo-controlled, crossover, and everything. They may have seen some benefits with the larger study with baby, because it was small sample size, yeah. and also maybe we do need to have a little bit higher concentration so we can get the second messenger effect, like with ghrelin, because that can potentially.
Which only seems to happen in water, correct? Not so much inhalation.
Yeah, it probably depends on the dose and how the profile, the concentration. But anyway, that's neither here nor there. So going to your question, yes, about the other study, because the first study that was done in 2013
was 52 weeks.
Yeah, you already talked. Yeah, so that one shows some great benefits on Parkinson's disease and decreased the unified disease Parkinson's disease rating score. So they thought, oh great,
we'll do a larger one over 80 weeks, which is actually how science is supposed to progress. And what I was asking Tyler is, it seemed the placebo group was taking hydrogen, so there was actually a smaller amount. There was no difference between placebo and the hydrogen group, but both groups saw a huge improvement over other studies in loss of Parkinson's disease score over the same period, which to me is very concerning. That should have never been published.
Well,
what are your thoughts? I
have a lot of thoughts, but there's some things I'd rather not say because I know that some of the details of that, and there's a lot of issues behind it. But I think that it is very unfortunate what happened, and I think I'll just say that if we consider that the placebo group, they did have hydrogen, and actually we've done some other study, work, and sometimes the placebo water actually had a much higher concentration
hydrogen,
because that's the range, and so it could have even had, 2 or 3 times higher concentration. And if you think about it, they're getting these bottles, and every other day they're getting maybe a high concentration of hydrogen, a very intermittent-like effect.
So it seems the bottles were mixed up, or something happened.
Something happened, and it was so. Anyways, what we'd look at though is there was no difference between the hydrogen group and the placebo group. And at the end of the study, yes, there was a decrease, but compared to other studies, the decrease was like
10 points less or something.
Yeah,
it was incredibly significant compared to other studies of the same duration, and both groups were actually taking hydrogen.
Right. So that study, okay. So that study, we can say, especially when we know more of the inner details, we cannot say that hydrogen does not work for Parkinson's disease. But we also cannot say that hydrogen does work for Parkinson's disease. Okay.
We need to do the study again properly.
And more of them. And actually, in science, can you ever say this works for this disease? You really can't ever get to that point.
This is a call to any public researchers. There's a reason why we've only been on the market 2.5 years. We have 2 published clinical trials. We have 2 more going through review that I want to talk with you about next, and 4 more underway. These are all public teams. What we do is we will donate all the product, placebo and hydrogen, and depending on the study, we might even donate extra funds for extra markers. We don't want to pay private teams to do these studies, but we want to know how this works, why it works, when it should work. So contact us. We'd love to work with you. We want to understand hydrogen better. If any of you want to study any of these things we've talked about or anything else, reach out to us.
Yeah, well, yeah, I that's great, and I appreciate you willing to work with our team and the other groups that we're working with, and the fact that you have no influence or call, no contract or whatever on whether or not the study is published or say in the results or whatever. That's important, and I hope that we can continue working with more researchers like this, and hopefully other companies will want to support this kind of research as well in the way that you are, so that we can just understand how it works.
I understand if you can't talk much about them, because I do understand the peer review process, but you were invited to be one of the authors on our third and fourth clinical trials, right? I know I've seen the data, you've seen the data. It's pretty interesting to me. I can't talk about it yet because they're both.
Are you talking about the non-alcoholic
fatty liver disease and the metabolic syndrome?
Yeah, so that one is kind of cool for me because so we just published a study before where what we found. We did diet-induced, so bad diet-induced fatty liver disease, fatty acid liver disease in animals, and we found that drinking hydrogen water was very effective at basically, improving the symptoms and preventing the damage and things. So in 2013, these researchers, they were trying to find benefits using alkaline ionized water. And so they contacted me. They were in the middle of doing their study, and they was like, "Hey, we just found out about you. We'd love for you to help." And so we started talking, and they showed me what they were doing. They had this, water ionizer machine. They got. They had, this very negative ORP, this negative oxidation reduction potential, as alkaline water, all the properties. And I was like, "Great. What's the hydrogen gas concentration?" They're like, "What? Why would we measure that?" And so I was like, "Okay, let's discuss this. But let's finish out the study because you can't just change the protocol right in the middle of doing. They're almost done with the study." And so I continued working with them. We checked all the controls. We finished the study, and lo and behold, there was no benefit, no effect between the regular water and the alkaline ionized water. And I was like, "Okay." That's kind of what I expected, but I wasn't so sure because we didn't know what the concentration of hydrogen gas was. The ORP was like negative 500 or negative 600 or something.
ORP is not a proper measurement. It only detects.
Yeah, yes, exactly.
It'll say if there is any amount of hydrogen in it, but you can get like a minus 600 ORP and have 0.03 ppm of hydrogen, which is not even measurable unless you significantly increase, with titration methods. And it's one of the things that drives me mad when I'm reading the research is how poorly some of the studies are written. And I know that's a big criticism often with new sciences. We need to remember when science is green, this is how it starts off. Small teams that maybe don't understand it properly, doing research, but then it advances over time. Hydrogen is new in a body of research growing. There's about 61, 62 published human trials and 1,200 publications. Yes. I've seen a study that one study on I think it was the newer one out of China on chemotherapy. The researchers indicated that you can't go beyond 0.8 ppm of hydrogen. They're just completely.
Yeah, I think there was probably some confusion with. Anyway, there was some interesting details on that one. But you're right. Unfortunately, with some of these green sciences, you get some articles that come in that have some quirky thoughts. But you get that even with well-established sciences. And I want to point out that although hydrogen has some of these things in there, especially going to the electrolyzed ionized water stuff, that kind of research. Lots of problems, but the research on hydrogen gas, the average impact factor, the credibility of a journal is often correlated by its impact factor. CIMAGO rating is better, but the average impact factor of the journals is around 3 for hydrogen, which is actually really good because typically if you're below 1, you're probably not a very good journal. You're probably some predatory open access journal or something. But if you're 1, 2 is a good journal. That's a stellar journal, and anything above that is really good. Nature Medicine is 27, and that was the first article that hydrogen gas published in. But I don't want to.
In this era, the first big one was in Science.
That's right, yeah, from Baylor University and Texas A&M. Yeah. Okay, but this study, so go back to this fatty liver disease. We finally developed the method with the titration. We got them the ability so they could do that, and they measured the concentration, and it was 0.1 or 0.2 ppm or something. So it was just too low. And so we repeated the same study, but we did a low concentration of hydrogen. It was, I think, 0.2 or 0.3 ppm. So pretty much the same concentration as what was in the alkaline ionized water, and also alkaline pH. So it's negative ORP and everything the same, and then just a higher concentration, which is not even that much higher, but it was like 0.8 or 0.9 ppm, right? And did the study, and the same study, and at the end, there was no benefit with the low concentration compared to just normal drinking water. There was no difference, but the higher concentration, obvious, clear benefits.
And this is sort of my understanding too. Is we don't fully know the dose-dependent response of hydrogen yet.
Yep.
And correct me if I'm wrong, but it seems that in many cases you need a higher dose for hydrogen to work, and in no case has a higher dose worked less.
Okay, that would be true. I don't know if in many cases a higher dose is needed. I'd have to think about how do we define that, because I mean, it's probably true, because the last part of the statement I think is very demonstratively true, even in cell culture, tissue, organs, and animals, humans, so on, that a higher concentration is never less effective than a lower concentration. And so the idea amongst researchers is there's likely a higher probability that a higher concentration is going to be more effective, and so let's go higher concentration. Now, the reason why most of the studies are between around 1 to 1.6 ppm is because at the time, that's as high as they could get. Like it was so difficult to get, and so when you come up with this pseudoscience garbage you're selling, but you come up with these tablets that are making such a high concentration, that's kind of opened up a new way to look at.
And I'm sure Tyler was joking.
Yeah. So it's still sometimes I'm like, that's so ridiculous. Let me measure that again. Yeah. Anyway,
it's like we've said, 10 ppm. In actual dissolved hydrogen is impossible, and that's what makes our tablet.
Yeah, don't
so
confuse.
unique.
It's actually not 10 ppm dissolved hydrogen. I think when we measured it, the concentration was around just over like 2.5 actually dissolved concentration,
which
and the
is
rest
still actually beyond, and that's what I was saying, that the cloud could create
because you have the high pressure, right? And so it follows Henry's law.
Yeah.
And then you can have high supersaturation that way, and then you have all the quasi bubbles, and that's why as you tell people, drink it while the cloud is present.
Exactly.
Right. Okay. Well, we've diverged a lot from the from the non-fatty acid liver disease, non-alcoholic fatty acid liver disease. So we found good benefits there, and then yes, when you contacted me again, and we're talking with the other group doing the research. We worked through this, and it's not published yet, so I don't want to
absolutely. But the other one that just finished, again, that was a bigger study that we did.
Yeah.
And we're seeing a lot of benefits there, but it still has to be finished right.
Well, and that one, okay. So first with the NFLD study, that one looked great. There was a really neat method that we used to look at the results. And it's pretty clear that hydrogen was having a great benefit there. So that'll be exciting when that comes out. And then the other study, what we see on the initial preliminary look at the data, clearly there are some very important biomolecules that were either increased or decreased, and that's important. Now I want to just be more cautious talking about that one, only because we haven't really completely gone through the statistical analysis with other correction statistics, just to make sure. But it looks very favorable, and I think we were talking about this. Didn't your partner say?
I don't want to make that comment to get him in trouble, but he was in shock.
Yeah, he's like, well, yeah, that's so that's kind of how I feel. But that's why I'm like, I kind of want to redo the statistical analysis and just confirm that this is what we found. But things are looking favorable for sure.
Great, and I want to ask you, because there is so much green science, there is so much flawed conclusions in the studies. I mean, I remember the first one that I read where I almost burst out laughing because it's so ridiculous, was that acute supplementation of hydrogen for vascular endothelial function, and they contributed the benefit to immediate direct scavenging of the hydroxyl radicals.
Yeah.
And I mean, serious scientists read some of these articles and they're like, "That's bogus."
Well, let's be careful. You know, they could be. They're also serious scientists, but that's not. They're okay. If you know the researchers, they're Japanese, but a lot of these are clinicians. You know, medical doctors, practitioners, not biochemists, physicists, chemists, people looking at this, and so they're serious. They
and
see.
That's a serious problem in science, by the way. Is a lot of specialties can't really speak to each other properly. So if you don't have the right specialists as part of the team, you can draw the wrong conclusions.
Yeah, so that's why we look at the results. Let's look at the results. Let's not worry about what was said. That's just rhetoric. That's just they're trying to take a story, right? Yeah. But you look at the results. You look at the data, and then you can determine from the data, this is what happened. So, I could say the same thing. Look, I see this great increase in superoxide dismutase, and I see this decrease in these, markers of, cell death, and it'd be like, and that's because hydrogen has the quantum frequency that resonates with the sun's, whatever. It's like, if somebody made that, you can't be so foolish as to throw out the valid data
exactly
because of a fallacious conclusion that was made.
And it's the same thing, and I apologize for saying serious researchers. What I meant to say is experienced researchers on that exact subject. You talk to a specialist in one field, and then you get them to talk in a different field, and they could come off sounding foolish because it's not their expertise.
Right, it's ultra-Kippadarianism. I mean, we're all kind of guilty of that, right? Where we basically, talk outside of areas of expertise, and we make these logical conclusions that for us are very logical on the surface, but seem absolutely absurd and ludicrous to someone who's an expert in that field.
And the first rule of the Dunning-Kruger Club is you don't know when you're in the Dunning-Kruger Club. It basically just talks about confidence and ignorance and stupidity, right? The less you know, the more confident you are that you know everything.
Right, yeah, exactly. Yeah, so that's why for scientists, when mature scientists, I think, mature scientists that are also humble, they don't care so much what was written.
They care about the raw data.
Let's just look at the data, and I can make my own decisions. It's not. We can do that, and that's how reviews are written. That's how we do things. Yeah.
So with all, say maybe small studies, all of these, issues that people bring up about hydrogen, what is the most convincing to you to spend your research on molecular hydrogen? What is driving your passion and interest? What do you see as the biggest sign that it's doing something?
Yeah. Well. Good question. I thought about this, obviously, and I don't know that I have the best answer for it, other than I enjoy it. I like being on this research, and sometimes, like I said to you, sometimes I look at this data and I'm like, what am I doing? This is ridiculous. Hydrogen having an effect, but then I go to the lab or I look at something and it's just unequivocal. Like what. We see the observation, we see the biological effect of hydrogen, and then that's what really gets me excited is, okay, how is it, what is the primary target of where is hydrogen, binding, like hydrogen receptor, that's ludicrous to me, but somehow hydrogen gas is having this effect, and I want to know how. So that's one of my major drivers. So I have two drivers. One is, how is it actually having these biological effects? Because we do see in cell studies, tissues, organs, humans, animals, I mean, all sorts of different animal models that hydrogen is having this biological effects. How is it doing it? And number one, it appears promising from these data, preclinical and clinical studies, that it actually can make a significant and important, meaningful difference in people's life, in your mother's life, your grandma's life, in my life. As an exercise enthusiast, I'm thinking, if I drink hydrogen water, I mean, I'm running, I'm doing like 80 miles a week right now in running and lifting weights and things. And so, yeah, that's insane. I know, it's
like
ridiculous.
130 kilometers for, our Canadian and Aussie and European and Asian viewers, everywhere outside the United States.
Yeah, that is an interesting, but I'm just saying, I think to myself, well, okay, the safety is very high, so, okay, we can look at this. Okay, so your question, what's the most convincing? Okay, one, we can see like data in cell culture and different things that are just really easy to be so you can repeat it, and it's so easy to repeat, and you just do it again, you can see the biological effect. Okay, that gives me confidence. And then when we see biological effects being reported from all over the world, you know, all throughout Europe, all throughout Japan and Korea and China, and then here in America. I mean, I talked about my conversation earlier with some of your professors here, or researchers here, and we're seeing the effect. And so probably just this preponderance, well, okay, I'm using the word lightly, you know, but this preponderance of different groups and organizations and individuals showing a biological effect, then yeah, that's probably to me the most convincing.
Because
that something's going
hydrogen
on.
isn't, you know, one maverick expert working on it. There are independent teams all over the world who are researching hydrogen, from North America to Europe to all across Asia, which is the bulk of the research right now, but it's growing here domestically. It's growing in Europe. So typically with a skewed, you know, topic, it's one or two groups with a commercial interest that are driving publications, and that's really doesn't seem to be the case with hydrogen.
Yeah, that's actually interesting. There's very little privately, you know, company-driven funded research on hydrogen. We just got a $250,000 grant from the Slovakia government, because I'm affiliated there, and to do research on a heart transplantation in pigs, and because this is something we're going to immediately apply to clinical use. I mean, this is where our funds come from, you know, from government grants.
Exactly, and it's, I mean, every study we're doing is coming from a grant here, or a university or a hospital that's funding it themselves. And some of the teams that are doing trials on us, I've offered to donate extra money for more measurements, and they said we don't need it. Right? Just send us the product. Right?
Well, I
mean, so it's predominantly publicly funded research going on with hydrogen by research teams, professors, clinicians that are truly interested in it and want to study it.
Yeah. And we can always use money, but I think sometimes we actually don't want to take the money. You know, for me personally, for example, because we want to be so sure that we don't subconsciously or consciously bias anything, as well as we want to get more grants, and we don't want there could just be some concerns, you know, during some earlier stages, and that's why some of the groups that we work with, of course, we can match, you know, the government will actually give us more money if we can get some funds to match that.
So one thing I want to address and ask you about, and it is a huge challenge for the public to understand, for the marketers to understand, even for the scientists to understand, the constantly changing story as we're gathering more evidence. First it was, you know, the selective antioxidant effect. I know there's been a lot of talk about altering gene expression. Has the story changed at all recently? Is there something I'm behind on?
Well, you know, changing stories
which isn't a bad thing. That means we're understanding it better.
Yeah, and it's also subjective. What does that mean?
It's hard for marketers, and it's hard for public to follow
that's
along.
Probably
but
the biggest story.
Science.
That's probably the biggest story that's been changing. You know, Dr. Otto would say the story has never changed. I know. Read his paper. You know, it actually doesn't talk exclusively about, you know, radical scavenging that's doing this and that. And he's said many times that it's you know, has these other effects, right? So in some people's mind, the story hasn't necessarily changed, but the people's perception of what the story is and understanding has changed. And so of course there's changes as we get more information, because we understand, okay, it's the signal modulator, we have alterations in gene expression. I think if we wanted to add another paradigm, and it's kind of a position that I'm championing.
Championing?
Championing. Yeah. I don't even drink. Anyways, I think that it would be that hydrogen is more of a hormetic molecule. It's actually, because there's no toxic.
It could be in the same, you know, instances. You know, H2S, you know, could have potential benefits for anti-aging.
Yeah, hydrogen sulfide, extremely lethal at high doses, but very small amounts.
Nitric oxide is a free radical.
Yeah, and of course that's critical for our vasodilation and normal cell proliferation and so on. So yeah, hydrogen gas, you know, because we don't see the toxic effects even at very, very high concentrations.
Even at 1,000 times the dose of what we're delivering you that could be used in deep sea diving, there's no toxic effects, correct?
Yeah, that we at least haven't been reported. We have to be careful. We can't say there are no toxic effects. What does that mean? You know, really, we're saying there have not been any reported. We've looked for them. We've looked at all the critical markers. I mean, this has been done from 1940s, looking at markers in humans.
And for our listeners, I like comparing, science as we gather more data and increase our understanding. How the story changes. It's similar to reading good philosophy or good literature or watching a great complex TV show. Every time you reread it or rewatch it, you take something more out of it and you understand the perspective of the author. And we can look at the data, the raw data, like the author. We're not understanding it in the beginning, and the more we collect, the more we reread it with the new data available.
The new information. That's what makes it interesting, because we can now look at the original data, because the data should still stand. The data should always be how it is. That now we can go back 10 years later with a new understanding and analyze the data in view of what we understand now.
And the picture becomes
some of the
clearer.
paradoxes, start making sense. Sometimes more paradoxes emerge. Sometimes like, okay, anyway, it's
going deeper down the rabbit hole. Tyler, thank you again so much.
Sure,
for
my pleasure,
and I hope everyone enjoyed our talk.